In this chapter, we'll be examining the autonomic nervous system and the visceral reflexes that are associated with it. We'll examine the effects of the system on the target organs, as well as the central control of this function. The autonomic nervous system is a portion of the nervous system that operates in a relatively secret or silent way. It manages a multitude of our unconscious or involuntary processes, and it's responsible for the body's state of homeostasis. Walter Cannon is an American physiologist who coined such expressions as homeostasis and fight or flight. He dedicated his career to studying the autonomic nervous system and found that it's more necessary to survival than are many functions of the somatic nervous system. The absence of an autonomic function is fatal because the body cannot maintain homeostasis without it. Let's review the divisions of the nervous system. You'll recall that the central nervous system consists of the brain and spinal cord. We've spent a chapter on each of these. Now we examine the peripheral nervous system, where we've seen a sensory and motor division. Both sensory and motor divisions have a visceral and somatic input. The somatic motor division, you'll recall, is about operating all of the skeletal muscles. The visceral motor division is about operating all of the viscera. This visceral motor division is further subdivided into sympathetic division and the parasympathetic division. The sympathetic division is what we call the fight or flight division, and the parasympathetic division is what we call the rest and digest division. The autonomic nervous system is a motor nervous system that controls glands, cardiac muscle, and smooth muscle. It can also be called the visceral motor system, as we saw here. The primary organs of the autonomic nervous system are all the viscera of the thoracic and abdominal cavities, and some of the structures in the body wall, like our cutaneous blood vessels, our sweat glands, and our piloerector muscles. Basically, any organs that need to be modulated during fight or flight or rest and digest, which are opposite functions. It carries out actions involuntarily. That means without our conscious intent or awareness. In contrast to the voluntary nature of the somatic motor system. This voluntary-involuntary distinction, however, is not as clear-cut as it once seemed. Because you probably recognize that we do have some control over these involuntary functions. We can choose to slow our heart rate by slowing our breathing. And some skeletal muscle responses are quite involuntary. Somatic reflexes are a great example. Now, visceral effectors don't depend on the autonomic nervous system to function. They only adjust the activity of the body's changing needs. So, for example, the heart will beat at a rate all on its own. But with the input of the autonomic nervous system, we can speed or slow its rate of beating. Now, we learned that if the somatic nerves of the skeletal muscle are severed, the muscle exhibits denervation atrophy. However, in the case of the visceral motor system, we'll see denervation hypersensitivity. That is, an exaggerated response of cardiac and smooth muscle. If the autonomic nerves become severed for some reason, they become extra sensitive to any stimulus. The autonomic nervous system is responsible for the body's visceral reflexes. That is, our unconscious, automatic, and stereotyped responses to stimulation. This is much like the somatic reflexes that we discussed in an earlier chapter, but involving visceral receptors and effectors. So we'll see that the pathway involves receptors or nerve endings that detect stretch, tissue damage, blood chemicals, or body temperature, afferent neurons that lead to the CNS, as well as interneurons in the CNS, and then efferent neurons that carry motor signals away from the central nervous system, and finally to the effectors that make adjustments to accommodate the situation. For example, if we look at the response to high blood pressure, or the baroreflex over here on the right, we'll see that blood pressure stimulates baroreceptors. Those baroreceptors send a signal into the brainstem that is communicated by interneurons to elicit a response through the vagus nerve, which transmits inhibitory signals to the cardiac pacemaker, and this decreases heart rate, thus decreasing the blood pressure. So as I've already introduced, there are two divisions of the autonomic nervous system that innervate the same target organs. These innervations may have cooperative or contrasting effects. In general, the sympathetic division prepares the body for physical activity. It is our fight or flight. So in the case of exercise, trauma, arousal, competition, anger, or fear, we activate the sympathetic nervous system. We have the same responses: increased heart rate, increased blood pressure, increased airflow, release of glucose into the blood, everything that prepares us to run from a situation. It reduces blood flow to the skin and digestive tract and puts it into the skeletal muscles. Now notice here, whether you're experiencing anger or fear or real trauma, we're still activating the same system. People that have difficulty managing their anger or their fear will have excess sympathetic response, but nowhere for the energy to go. In the case of exercise, we're activating all the same responses. In the case of trauma, all the same responses, but we have somewhere to go with them. If we're threatened by a bear, we run and activate the sympathetic division. If we experience something that elicits a sense of fear, we activate the same sympathetic division. Sometimes weird things initiate fear for us, like competition or fear that we won't win an argument, perhaps. Here we're activating the sympathetic division, causing all these increases, but we're not actually going to run. It's not helping us. So this energy gets trapped in our body. This energy that gets trapped in our body and can't escape because we're not actually running manifests itself as disease. One of my primary yoga gurus says that disease is the same thing as dis-ease. In contrast, the parasympathetic division of the autonomic nervous system is the rest and digest system. It calms many of the body's functions and thus reduces energy expenditure and assists the body in its daily maintenance. It involves digestion as well as waste elimination. You can think of it as after a big Thanksgiving meal, laying on the couch. We're definitely at the paramount of parasympathetic division action. Do note that this doesn't mean that the body alternates between states where one system is entirely active or the other system is entirely active. Normally, both systems are active simultaneously. They exhibit a background rate of activity that we call autonomic tone, which is a balance between sympathetic tone and parasympathetic tone. It shifts in accordance with the body's changing needs. Remember, it's very dynamic. In parasympathetic tone, we'll see maintenance of smooth muscle tone in the intestines, holds the resting heart rate down at about 70 or 80 beats per minute. The sympathetic tone, in contrast, will keep most vessels partially constricted and thus maintain blood pressure. This is even in a resting state. The sympathetic division will then take over in the case of fight or flight and excite the heart. However, it'll inhibit digestive and urinary function because you don't need to waste any energy there while we are running from something that's creating fear. The parasympathetic system has the opposite effect. It will activate the digestive and urinary function and inhibit the action of the heart. Remember, these two systems are both constantly working together to create the homeostasis that allows us to live. So the autonomic nervous system has components of both the central and peripheral nervous system. It includes a control nucleus in the hypothalamus and in other brainstem regions, as well as motor neurons in the spinal cord and peripheral ganglia. It also has nerve fibers that travel through the cranial and spinal nerves. However, there are some differences. In a somatic motor pathway, we'll see that the motor neuron extends from the brainstem or spinal cord, and it issues a myelinated axon that reaches all the way from the spinal cord to the skeletal muscle. However, in the autonomic pathway, the signal needs to travel across two neurons to get to the target organ, and it must cross a synapse where these two neurons meet in one of the autonomic ganglion. That means there's a presynaptic neuron that has its soma in the brainstem or spinal cord, and the axon goes to an autonomic ganglion. Here, it synapses with the postganglionic neuron, whose axon extends the rest of the way to the target cell. This postganglionic neuron is unmyelinated. Sometimes the autonomic ganglion will be very close to the spinal cord. Sometimes it'll be very close to the target organ. We'll examine these different pathways shortly. For now, pull out a piece of paper and write on it sympathetic system and parasympathetic system. Write as many things as you can remember about the sympathetic system and as many things as you can remember about the parasympathetic system. Get your brain to be a little bit curious. Once your brain is a little bit curious, you can go back into your notes and seek some of the things. Next, make yourself a list of the different visceral organs that you can think of, and note down whether you think they would be activated by the sympathetic nervous system or the parasympathetic nervous system. It's going to be important for our diagramming assignment later in this chapter.